Okay, everybody. Welcome. Okay, so the plan for today is to finish chapter 9. There was just a few more things. I want to spend the first 15 minutes or so reviewing chapter 9, kind of summing up anything I missed. We had a conservation of angular or rotational momentum question where the two solid disks collide inelastically. So we'll do that. And then we're starting in on oscillations, so our vibrational motion, as they call it. And we'll talk a little bit about simple harmonic motion and modeling this vibrations with a cosine curve. So that's what's on the schedule. We got, Tiffany's got the wireless mic, so you can click on, type something into the ed discussion under classes topic, and she can read that out if she wants, or any questions anybody has, you can shout out also if you want. It's getting a little, there's fewer of us, so it's sort of easier for me to deal with questions. It's always the case. So, I got a question for you. And it's easiest solved, I think, thinking about this rotational kinetic energy and actually the kinetic energy. If you were to have an object that was sliding along and then it went up the hill, then that 1/2 mv squared would be converted into mgh as it goes up the hill, right? You'd have that balance of energy. Same exact thing is going on here, except it's rolling without slipping. Meaning that as it's going, so when it stops, all of its kinetic energy goes away if it's rolling without slipping, right? So you know kinetic energy, all the kinetic energy goes to 0 at the top because omega will go to 0 and v. But when it's at the bottom, it has two things. It has 1/2 mv squared and 1/2 I omega squared. And v is equal to r omega, I think. So we read it out. An iron hoop and a wooden disc of equal mass and radius are rolling without slipping on the flat ground. The equal speed is shown. The hoop rolls without slipping up an incline, elevated at an angle θ1 above the horizontal, and reaches a height h1 before it stops. The disc does the same thing, except it goes up a different angle, θ2, and it gets to a different height, h2. So the question is, how do those heights compare? Is h1 less than h2? h1 bigger than h2? Are they equal? Or it depends on these angles? Yep, question?
Answer A is broken.
Oh, that's weird. I'm getting 39% of you have answered it, according to this. Oh, I see. It doesn't say what it's supposed to say. Yeah. So what A is supposed to say is H1 is less than H2. I don't know if I can change that at this point. So on your screen, A is a typo, but just use what's on the front here. What I meant there is H1 is less than H2. Okay. So please discuss, pair up, see if you agree with your neighbor. Give you 1 minute. You guys remember these? Probably should have mentioned that. The rotational inertia of the solid disk is less than the rotational inertia of the hoop. If you didn't remember that, that's hard to do. How you guys doing? You want to click a guess in here? Maybe 5 seconds. 4, 3, 2, 1. Concept here is conservation of energy, I think. They both end with 0 kinetic energy. And so I think the hoop should get a little higher, I think, because it has more kinetic energy to start with. They're both going at the same speed, right? So E initial here is 1/2 m times v squared plus 1/2 I omega squared. So it's actually equal to 1/2 m v squared plus 1/2 times m times r squared times v over r squared. Whereas for this one, E initial is equal to 1/2 m v squared plus 1/2 times 1/2 times m r squared times v over r squared. So this one starts off with less energy. Right? E02 is less, so the H2 is going to be less than the H1. Solid disk begins with less rotational kinetic energy. Same translational, so it won't get as high before it stops. Questions on that? Anybody want to talk about the term test a little bit? It's because it's a little confusing. There's 3 marks posted, but let me just tell you. So there was mark. So there's 3 things. One is the multiple choice mark out of 20, and you have to add these 3 marks to get a mark out of 28. The long answer is out of 8, but then there's another number which is confusing, and so it's called term test 2 boost. It's a bonus mark, so it doesn't increase the denominator. The denominator is still at a 28, but the boost adds to the multiple choice and the long thing, and it's this. So X is your raw mark out of 28. And there's the absolute value of 14 minus X, which has a maximum when, so 14 minus that has a maximum when X equals 14. So if you got 14 out of 28, you got the maximum boost. You're going to get 17 out of 28. If you got 0 out of 28, you get 0. If you got 28 out of 28, you get 28. So 0 maps to 0, 100% maps to 100%. And then in the middle, everyone got a kind of boost. And so basically the mark is the sum of the 3 things you see, just add them up, and it's out of 28. It's called a triangular boost. Got it? So why the hell did I do that? Well, what I wanted to do is to make the 2 term tests kind of same histogram, basically. So I did. That's why I did that. Term test 1 had already a bonus point for following instructions, and the average was 70, median was 71.4. So with this triangular boost, things look kind of similar for term test 2. A little bit higher median, a little bit lower average, but similar kind of thing. It's about as similar as I could get it without doing some ridiculously complicated function. And congrats to the 34 who did perfect on term test 2 and the 130 of you who are in the A+ range on term test 2. So it's a weird thing, you know. This struck me the first semester I was at university, is that I was, you know, one of the definitely top students at my high school, and I got to university and everybody around me was among the top students at their high school, right? So all of a sudden, things are a little different. You got these crazy. Look at these. Look at you guys. Look at all these A's. Anyways, it's crazy. And these are difficult things. So there you go. You should have got an email either, I think this morning the GradeScope email came in about the long answer, and then there was another email a few days ago about the multiple choice. But take a look, just make sure we didn't make any mistakes. If you do find a mistake in the marking or the computation of your mark, you can just click on the regrade thing on GradeScope and let us know what happened there. Or you can email. You know, I guess the first thing you should do if you have a concern is really carefully look over all this stuff I posted. I wrote out the solutions, and there's a 45-minute video of me talking about what I think the reasoning is behind these solutions. So make sure you've at least listened to that. But if we've made a mistake, we will definitely fix it as soon as possible. I don't want to have any mistakes there. Okay. How are we doing, Tiffany, with the discussion board? Anything blowing up there? You're good. Okay. Okay, so just to finish up with chapter 9, remember this whole, let's do an example of conserving rotational momentum. So we were going to do this last time. When do you conserve momentum? You conserve momentum, linear momentum, when there's an inelastic collision. Remember that? So when you have two carts and they collide together and they stick together because of Velcro or stickiness of some kind, or the Hummer and the Toyota collide together and stick, then the way you solve that is you conserve momentum. And that certainly happened on the test, didn't it, in the written question of the test. First you conserve momentum, just to get what happens during that inelastic collision, and then after that you might do kinematics or whatever. So this is a conserving rotational momentum question. A 20 centimeter diameter, 2 kilogram solid disk is rotating, so we can draw that here, at, I'll call this number 1, V initial, maybe 1, is 200 rotations per minute. Okay. And then a 20 centimeter diameter, 1 kilogram circular loop is dropped straight down. That's a little harder to draw. I don't really have a lot of art skills, so just bear with me. It'd be like a donut. We're going to call this 2. And the omega initial of 2 is 0. So R1 equals R2 is equal to 0.2 meters. M1, the bottom thing is 2 kilograms, and M2, the hoop, is 1 kilogram. So we're going to assume, so what happens is that it's dropped down, friction causes the loop to accelerate until it's riding on the disk. What is the final angular speed of the combined system? So we're going to assume here a totally inelastic collision. And we're going to conserve momentum. Except we're going to conserve the rotational momentum. Because there's no external torque. External torque. They will torque each other up, but nothing on the outside. So what this means is rotational momentum is conserved. So Li equals Lf. That's how we're going to do it. And remember here that L is equal to I omega, and I1 is equal to 1/2 M1 R1 squared, and I2 is equal to just M2 R2 squared. Does that show up? You guys know where those equations came from? This is that table, 9.3. So the loop has MR squared with no fraction out in front, and the solid disk has 1/2 mr squared. So that's it. So do L initial equals L final. You've got 1/2 m1r1 squared times omega initial 1 plus 0, because the top thing isn't rotating, equals, they're going to rotate together. So it's 1/2 m1r1 squared omega final plus m2 r2 squared omega final. I'm just going to add them up as if they're, oops, not squared. Don't square the omega. Just going to add them up. Same as you would do with the Toyota and the Hummer. They're now together, and they both have the same final velocity. So R1 equals R2. Let's say it's equals R. Divide both sides by R squared over 2. And I get that M1 omega initial 1 is equal to M1 omega final plus 2 M2 omega final. So solve for omega final, which is what you're trying to find. It's M1 divided by M1 plus 2M2 times omega initial 1. So it's 2 kilograms divided by 2 plus 2 times 1 kilogram times 200 RPM. So omega final is equal to 100 RPM. Half of initial omega. Questions about that one? There was one more thing I didn't do last time, which is the analysis of that demo with the rolling without slipping down an incline. So why don't we do that? It was this. You remember we had the hoop versus the solid disk. And what you hopefully saw from the video, these are just screenshots from yesterday's video, Monday's. The disk always wins. So why is that? So what I want to tell you guys is you have all the skills that you need to solve these problems. It's just Newton's second law. And so basically the steps are, step 1, sketch, draw a diagram of the situation. Step 2, do a force diagram. But the force diagram will be extended because now torques matter. Step 3, write down all your Newton's second laws, and then solve it out for whatever you're trying to find. You guys can do this. And I guess you could watch me do it, but it's so basically sketch it. You got this thing rolling down. It's some sort of circular object. Its radius, we'll call it R, capital R. Its mass, let's call it M. And let's do rotational inertia in a general sense. Remember how there's always a fraction? Why don't we just call that fraction x? I is equal to x times m times r squared. Sometimes x is 1 if it's a hoop, or it's a half if it's a solid disk, for example. So where x is some fraction that from a table. I think it's called table 9.3, right? Depending on the shape. Is that it? Anyway. Point being, we can tilt our axes as we always do. There's y, there's x. We're going to have, don't forget your rotation axis. We'll have counterclockwise, will be positive rotation. So the whole thing's going to accelerate downwards, ax, ay equals 0, and alpha will be negative, I guess. That's the only... Unfortunately, the way I've drawn this thing, the whole thing has to rotate clockwise, I guess, to accelerate down the hill, but that's okay. So basically, AX is positive, because it's rolling, plus X direction. That's why we tilted our axes. And alpha is negative, so that's okay, for clockwise acceleration, rotational acceleration. So basically, I'm just going to say this is my acceleration constraint, is that alpha is equal to negative a sub x divided by r. And it's going to be one of my equations, so I'll just call it that, equation 1. And the system here, by the way, that you're going to draw a force diagram of is the round object. So let's just draw it. Force diagram. It's a circle, and there's a middle. I'm going to assume that the center of mass is this rotation axis, the center. So let's draw the forces on it. We've got mg. Any other forces? Yep. Right. So I think that's acting here, right, where it's touching the ramp, and that will be perpendicular to the ramp. So in fact, I think the normal force. The force line of the normal force goes through the rotation axis. Are there any other forces? I can think of one more. If it's rolling close. So, yep. Yeah. So, but what is it? Kinetic friction or static friction? Static. Correct. Nice work. Put you on the spot there. That's you're absolutely correct. And wait, so that's the other thing. Is it going up the hill or down the hill, this force, static friction? Where should I draw it? Yep. Why? Amazing, you guys got it. So if it was not rotating, if it's just going to slide, it would want to slide down, so static friction prevents it from slipping by acting up the hill. Amazing. So that's it. I think those are all the forces. And the other thing is that the whole thing's going to rotate counterclockwise, so I think static friction is what's providing the torque here. Okay, let's go back to blue here. So if the center is the rotation axis, as I've defined it here, it's kind of weird because the rotation axis is moving, but that's okay. The lever arm for N and mg are 0. The force of gravity acts on the center of mass, which happens to be the rotation axis, so that clearly can't provide any torque. And as it turns out, the normal force, if you look at that force line, because it's perpendicular to the surface and it's a circular object, I think the force line of the normal force is going to pass right through the center. And therefore, it's not going to torque it up either. So basically, only F sub s provides any torque. Okay? And also, it's going to slow it down. Fs is in the negative x direction, so let's not forget about that. And what's in the, so why would it go down the hill? Is there anything in the plus x direction? What? Exactly. Okay, so there's a component of mg, and say a component of, it's probably going to be mg sine theta or something, mg in plus x. So that's good. So just write down Newton's second law, which is the sum of the forces in the x direction is equal to the mass times a sub x. So what is it going to be? It's going to be mg, so there's mg is on the diagonal. Remember all this stuff? There's your theta, there's your negative fy, here's your fx. So there's a, hopefully you guys have done this enough times to know it's mg sine theta minus fs is equal to m times ax. So that's an equation. I'm going to call that equation 2 because it'll be useful. And then also, the sum of all the torques is equal to I times alpha. So it's Fs times R. So wait, Is it a negative torque or a positive torque? Remember, it's to the left, so it's clockwise. I think so. This should be a negative torque, so put a negative sign there. And then I is x mr squared, and then times alpha, and we can call that equation 3. And now we've got 3 equations, 3 unknowns. We can just solve this out for whatever we want. 3 unknowns. One's the acceleration constraint, which went off the slide there. You got Fs, you got alpha, and you got Ax. So the strategy here is just to eliminate Fs, which you don't care about, and alpha, and solve for A sub x. So first we can plug equation 1. Remember what that was? That A is negative alpha is negative Ax over r into 3. So you got negative Fsr equals xm, oops, where's my negative sign? R squared times negative A sub x divided by r. Okay, and I can divide both sides by r, because there's actually there's a bunch of canceling, right? This squared cancels this r, and then this r can cancel this r, and you just end up with, it doesn't matter what the radius is, you get that Fs, and there's negative signs on both sides, so you just get Fs equals x times m times A sub x. And I'm going to plug this into equation 2. So I got m times g times sine of theta minus x times m times A sub x equals m times A sub x. It's easy to get screwed up with the negative signs in this, but divide both sides by m. But anyway, I think I get g sine theta minus x ax equals ax. So g sine theta is equal to a sub x times 1 plus x. So a sub x is equal to g sine theta divided by 1 plus x. And that's a general solution for anything that's circular or has a circular cross-section that's rolling down an incline without slipping. Using all the skills that you guys have learned over these past 9 chapters. So it could be a handy thing to have in your read sheet, I guess. We can easily now solve all this stuff. Remember, so this is what we just found out. Frictionless ice cube was just A equals g sine theta, because there's no friction. If there's friction, then the solid disk will be A is equal to g sine theta divided by 1 plus a half. And then the hoop will be g sine theta divided by 1 plus 1. Or a glass marble will be A equals g sine theta divided by 1 plus some other fraction. Does anyone remember? Solid sphere was 2/5 mr squared, so 2/5, etc. But anyway, this is less. Hoop accelerates slower than solid disk, which is why solid disk wins. And that's my last chapter 9 slide. What time is it? We're doing okay. All right. Maybe we'll do the basically. So this is it, which is that we've been studying linear motion, objects moving 1D or 2D at either constant velocity or constant acceleration. And we've also studied objects that are rotating or moving at constant speed in a circular motion. In this chapter, we're looking at things that vibrate back and forth. Just off the plate, right? Yeah. So, simplest example is maybe the pendulum. So right now, this mass is at an equilibrium, meaning that there's all the forces on it cancel each other out. There's gravity and there's tension, that's it. But if I pull it to the side and release it, it starts to, it's called vibrate. So what's happening is that if it's here, then the combination of tension plus gravity puts a net force on it, which is towards equilibrium. Or if it's over here, the combination of gravity and tension also puts a force which is towards equilibrium. It's sort of weird. If it's over to the left, it gets pulled to the right. If it's over to the right, it gets pulled to the left. And it's only if it's hanging straight down that all of a sudden the force is zero. So you got it's called a restoring force. No matter which way you push it, if I push it to the right, it wants to go to the west. If I push it to the left, it wants to go to the right. So, but when it gets to the middle, it doesn't stop. Because it just has a velocity now. And so it overshoots the equilibrium and gets to the other side. And that's why it oscillates back and forth. It has zero acceleration at the center, but it has non-zero velocity. And so the velocity flips back and forth and it does this oscillation. Same thing can happen with a mass on a spring. So right now, the spring force is equal to mg. But if I pull it down, the spring force is greater than mg. And so we'll want to accelerate upwards. Or if I lift it up and the spring force is less, then mg is now greater. So it wants to accelerate downwards. So there's some middle position called equilibrium where it always wants to accelerate towards. So if I look at this, it'll oscillate around equilibrium. And so that's the same. It's actually, there's very similar motion happening with the pendulum and with the mass on the spring. So that's the gist of it. We're going to try to explain this whole thing mathematically, which turns out to be the trick. But, okay. Vibrational motion is periodic back and forth motion of some part of a system that occurs when that part is displaced from equilibrium. Okay, and there's some forces that try to restore it. So examples, sloshing of water in the bathtub, swaying of a tall building. It turns out that if you go into the top of McLennan physics labs, way up to the 14th floor there, astronomers have measured there's about a 1 second period of the whole thing, especially on a windy day. It goes back and forth, which is annoying if you're looking at stars. The pendulum of a grandfather clock, like this little animation. The vocal cords in your larynx, if you actually hold your finger to your throat and go, you feel a little vibration. And that is one of these oscillations. It's happening inside your, let's do it together. 1, 2, 3. You feel a little vibration there? That's what's actually creating the sound, is that there's a vocal cords inside there, and when the air passes over them, they're vibrating. So vibrations are all over the place, and it's really important in physics to describe them. It starts with frequency. So frequency and period are inversely proportional to each other. The time to complete one full cycle on one of these oscillations is called the period. And 1 over that's the frequency. And frequency, if you measure a period in seconds, the frequency is in Hertz. So 1, sometimes Hz is what it's called. 1 Hz is equal to 1 cycle per second. 1 full time around. Let's do another, hopefully not screwed up. Learning catalytics. Give you a minute to think about this one. Is it possible to have less than 1 hertz? Yeah, I'm just making a physics joke here. That's a joke because I don't think that Hertz is a plural thing. It's the last name of some person who studied vibrational motion, I guess. So 10 seconds. Just click in your best guess here for period. Okay. Do stop. And laptop 2. You be quiet. Excellent. Okay, so that's just 2 seconds. That's sort of what's being shown there in this little animation. And the way to do it is just use that frequency. Frequency equals 1 over period. You can't use that. Period is equal to 1 over frequency. And 1 divided by 0.5 is equal to 2. And don't forget the seconds as the SI unit. So B. And let's see if we can just fire up this. The sort of canonical vibrational motion is a horizontal mass on a spring. So this is showing a spring that can be compressed and stretched, and the thing just oscillates back and forth. Okay, so that's the idea that we'll most often look at. There's an equilibrium position, which is where there's no force on it. When resting at this position, then there's no acceleration. But during vibrational motion, whenever it gets to that position, it's moving. And so having non-zero velocity, but zero acceleration, means you keep going, you overshoot. Restoring force comes up here. That just means it's a force that's always pointed towards the equilibrium position. So if you go to one side of equilibrium, you get pushed back to equilibrium. Go to the other side of equilibrium, you also get pushed back to equilibrium. And that also, furthermore, the farther you get from equilibrium, the greater that force is. So as you more and more stretch the spring, that restoring force increases linearly with the distance from the spring. That's going to be important. And then amplitude, this is an important vocab thing, is that the maximum displacement of the vibrating object from its equilibrium position. So for example, if you've got like a wall and a spring, and you've got a mass, if it goes sort of back and forth like this, to this position and this position, then it's half that total distance. This distance right here is called the amplitude. Okay? And that the maximum distance from minimum to this is actually 2a. So let's actually look at some tracker graphs that I did. So I put a mass on a spring and then tried to measure the position using that tracker software, and I got this graph. So what you can't really see here is the times 10 to the minus 2. So this says 6 down to minus 6, and it says meters, but don't forget it's times 10 to the minus 2. So these are actually centimeters on the vertical axis. It didn't go very far. It was on my table, so I was just measuring it back and forth. And I recorded it. I clicked numbers until I got up to a little more than 2 seconds. And I got this nice graph. So from this graph, can you tell me what the frequency is? Check your neighbor. And the next question I'm going to ask you is going to ask for the amplitude. How do you do this? I don't know what it is here, maybe 1.25-ish, something like that. It's a little hard to estimate, but go once, go twice. You guys have frequency? And stop. Survey says 83% of you are saying B, that is 0.8 hertz. Yeah, so that's probably right? It's going to be F is going to be 1 over 1.25-ish. So I don't know how that works, but the closest answer here is definitely B. Maybe it's a little hard to estimate. I'm not quite sure if it was released exactly from rest. It looks like it was kind of moving a bit there. So, but anyway, do you have an idea, for the amplitude? One more minute. Feel free to check your neighbor, and you got 50 seconds. And can you just click in 10 seconds? Okay. And survey says, this one was a little, wrong. Stop. And so it's a little more controversial. There was C or A. I liked A. Basically 6 centimeters. So there's the 10 minus 2. And I guess the main thing there is that it's not 12 centimeters. 12 centimeters is the maximum, I guess, displacement. But it's half that gives you the amplitude. So, okay, so so I'm an experimentalist, and I like to do these kinds of experiments. So what we need to do now is be theorists and try to work out the theory of what's going on here. And that turns out to be the difficult part. So, okay, let's do the simplest possible thing. Forget about gravity. We'll have a frictionless surface, and you've got a spring with a mass attached at one end, and the other end's attached to a fixed wall. When it returns to equilibrium, so you release it, you stretch it, release it. When it returns to equilibrium, is it at rest? Or will it be moving, or it be at rest? It'll be moving. It won't be accelerating because the net force is 0 at equilibrium, but it's going to still have inertia, which carries it past equilibrium to the other side. So okay, so we got that. So to analyze this motion, let's first define our coordinate system. So we'll put x equals 0 at equilibrium, just for ease. So there it is. So now we've got a restoring force. Hooke's law is negative k times x. So if that's the net force, then you've got Newton's second law. So I can plug that in. And I got A is equal to negative k over m times x. So this is the problem, is acceleration, remember what is it? It's the rate of change of velocity. But what is velocity? Velocity is the rate of change of x. So this is a second order differential equation that really is not at all easy to solve. The slope of x equals a negative constant times x. So you've got kind of x's on both sides, and it's really it's pretty nasty. It's weird. It's not constant acceleration is my issue here. You can't use any of these equations of constant acceleration. So why we started up a whole new chapter on this. So kinematics won't work. Well, here's again, I'm not that smart, so what I like to do is try to break it down into something I can solve. What if we do just a little bit of time and see what happens? Well, if time is very small, then maybe acceleration is constant. And maybe even you could say if it's small enough, the velocity is constant. So if the acceleration is almost constant, then anyways, you could use an equation of kinematics to say that the final velocity is the initial velocity plus a times delta t. And then when it moves, you can do x is equal to old x plus v times t, because you kind of know v roughly, and you kind of know a roughly. So you can find the new x, and then when you have the new x, you can then find the new value of acceleration, and just kind of step through it. So we could try it. I did the whole thing on a Google spreadsheet. So we can try that. So the pink numbers are what I'm inputting. So let's say it starts at 1 meter, you release it. And it starts with release it from rest. Well, the acceleration is equal to, what is all this stuff? -1 times F3, that's the spring constant, times B2, which is the position, divided by F4, which is the mass. So it's a 1 Newton per meter spring and a 1 kilogram mass. So then I use Control C and Control V and update the new acceleration based on, what's this? So x is the old x plus c2 times f2. So c2, is the old velocity, times f2, which is the time step, the delta t. So you're always multiplying by the delta t times the velocity gives you a new position. And then similarly, the new velocity is the acceleration, the kind of most recent acceleration times the delta t. Anyway, so that's called numerical integration. So why don't we just Control C all these things and just keep doing it. Can I do Shift? Let's do like 1,000 of these. And do Control V, just fill it all up and see what actually happens and graph it. And look at that. It just looks like, does it look like anything to you? Look at that. It looks like cosine. And what's even weirder is that, look at this point down here when it gets to its maximum lowest position. What time is it when it gets to its lowest position? It kind of went down to minus -1 almost. Oh, it overshot 1 a little bit. But where did it get lowest? Maybe right around here somewhere, right? 3.14 at pi seconds. So I can actually compute pi with this incredibly simple little thing. So anyway, there's some motivation right here from this Google spreadsheet to make me think that maybe the answer is cosine. I don't know. And what's weird is that nobody ever really solves it any better than that. They just tell you at some point in math class that the trial solution is cosine. So we can work that out, but anyway, we're just going to tell you. You could also use sine, depending if instead of dropping from rest, you could give it some initial velocity at its equilibrium position. But anyway, this is called trial solution. I'm here to tell you a lot of very brainy calculus people tried to solve the equation above, but in the end, as far as I can tell, they all guess. And they all guess cosine. And then they just move on. So that's how you do it. It's called simple harmonic motion. It's a mathematical model of vibration. And we're going to talk more about it on Friday, graph it out. But just once again, thinking about this, if something's moving with like a simple harmonic motion, if you look at all these points, at which points does it have the greatest and least speed? At which points does it have the greatest and least magnitude of acceleration? And at which points does it have the greatest and least magnitude of the restoring force? You should think about that. I'll talk about that more on Friday.